The bore is a hole. That's all it is. A cylindrical hole bored through the center of a solid iron casting, 3 feet in diameter, 4 feet long, the interior surface machined smooth, the diameter uniform from end to end within a tolerance that, in 1774, nobody in the world can consistently achieve. A hole, an absence, the space inside the cylinder that the piston moves through, that steam pushes against, that converts heat energy into mechanical motion. The most important shape in the Industrial Revolution is not a shape at all. It's the space inside a shape. If the precision that made the Industrial Revolution possible fascinates you, subscribe now. This hole in this cylinder is the most important shape in engineering history, and the story of who measured it is extraordinary. A hole is not nothing. Myfanwy Holt knows this because she measures holes for a living. Her gauge, a cylindrical tool of her own manufacture, 2 flat contact surfaces connected by a dial calibrated in thousandths of an inch, slides into the bore of every cylinder that leaves the Bersham Ironworks. She turns it, reads the dial at 4 points around the circumference, compares. If the readings are equal, the bore is round. If they differ, the bore is oval. And an oval bore means steam leaks past the piston, and a leaking piston means the engine wastes fuel, and wasted fuel means money lost on every stroke. A hole is not nothing. A hole is the shape of what's supposed to go in it. The piston, the cylindrical plug that must fit inside the bore with enough clearance to move freely, but not enough to leak. If the piston diameter is 36 inches, the bore must be 36 inches plus a tolerance, the gap between piston and cylinder wall that allows motion without leakage. Before Wilkinson, that tolerance is 1/8 of an inch. After Wilkinson, it's 1/100th. The difference? Roughly the width between your fingertip and the sensation of touching something is the difference between a working engine and a failing one. John Wilkinson, Iron Mad Wilkinson, the man who wants iron to be everything, who has commissioned his own coffin in iron, who plans to build an iron boat. It'll float, he says. People laugh. It will float. Stands on the foundry floor at Bersham and watches the boring machine work. The bar, 12 feet of iron rotating at 30 revolutions per minute powered by a water wheel, enters the raw casting at one end and emerges at the other, cutting a cylinder of accurate bore from a rough casting of indeterminate interior. A visitor, a naval procurement officer examining the cannon that Bersham also produces on the same machine, asks about the coffin.
You want an iron coffin?
Iron boat too one day. Iron bridge. Iron everything.
People will think you're mad.
They already do. They call me Iron Mad. I consider it a compliment.
Before Wilkinson's machine, a cylinder is bored like this. The casting is mounted on a lathe. A cutting tool is inserted through one end. The tool is advanced by a screw mechanism, removing metal from the bore surface as the casting rotates. The problem: the casting is supported at one end. The far end sags under its own weight. The bore, instead of being perfectly cylindrical, is slightly tapered, wider at the supported end, narrower at the unsupported end. The taper is small, 1/16 of an inch over 4 feet, but it's enough to ruin a steam engine. Wilkinson's innovation is mechanical and conceptual. Mechanical. The boring bar is supported at both ends, passing through the casting, guided by bearings on either side. The bar can't sag because it's supported at both extremities. The cutting head, mounted on the bar between the bearings, travels through the stationary casting, removing metal in a perfect cylinder because the bar's alignment is maintained by gravity, not gravity. Conceptual. Previous machines rotate the casting and keep the tool stationary. Wilkinson rotates the tool and keeps the casting stationary. This reversal seems minor. It's revolutionary. A heavy casting, when rotated, wobbles. Its mass is unevenly distributed. Casting isn't perfect. And the wobble is amplified at speed. A lightweight boring bar, when rotated, is stable. Its mass is uniform. The bar is machined, not cast, and the rotation is smooth. Myfanwy calibrates her gauge against a standard, a turned steel cylinder of known diameter, machined at Bersham's lathe to the highest precision available. The standard sits in her gauge room, the clean, quiet room with its north-facing window and its surgical arrangement of measuring instruments. She checks the gauge against the standard every morning. The standard doesn't change. The gauge might. Temperature affects metal, expanding or contracting it by thousandths of an inch. Room temperature, steel temperature, the temperature of Myfanwy's hands, warm fingers fingers expand the gauge slightly. Cold fingers contract it. She holds the gauge for exactly 30 seconds before reading, allowing it to reach thermal equilibrium with the standard. Gareth Collette doesn't care about thermal equilibrium. Collette is the cannon maker, Bersham's military business, the original business, the reason Wilkinson built the boring machine in the first place. Cannon, iron tubes bored true so that cannonballs fly straight, travel far, and hit what they're aimed at. Precision kills. A cannon bored 1/8 of an inch oversized wastes gas around the ball. Reduced range, reduced accuracy. A cannon bored true, tight around the ball, the gas sealed behind it, fires farther, straighter, deadlier.
Your gauges serve one purpose, Miss Holt. Better cannon, better killing. Everything else is a byproduct.
He's right. The boring machine was built for cannon. The precision was developed for war. The same cutting head that bores engine cylinders, the cylinders that will power factories, pump mines, spin cotton, grind grain, also bores the barrels of weapons that fire iron balls through the hulls of ships and the walls of fortifications. The contradiction is the machine itself. One tool, two purposes. The destructive and the constructive coming from the same bore. James Watt needs a cylinder, not a cannon, a cylinder, 3 feet in diameter, bored true. True enough that a piston can move inside it without leaking steam past the edges. True enough that his separate condenser, the innovation that makes his engine efficient, can function as designed. Without a true cylinder, the condenser advantage is lost to leakage. Without a true cylinder, the Watt engine is theory, not practice. A woman with a gauge and a steady hand measured the cylinders that made steam engines possible. Without her accuracy, Watt's efficiency is theory. If you want to know how the Industrial Revolution was measured into existence, subscribe. The cylinder is cast in Bersham's foundry. Molten iron poured into a sand mold, cooled for 3 days, the mold broken away to reveal the rough casting. A hollow cylinder, approximately 3 feet in diameter, approximately 4 feet long, with an interior surface as rough as a cave wall. The boring machine will transform this rough cave into a precision bore. The boring bar enters the casting. Wilkinson's machine, both end support, rotating bar, stationary casting. The cutting head advances at 6 inches per hour, painfully slow, but speed means vibration, and vibration means inaccuracy. The iron shavings curl from the bore like metal ribbons, long, thin spirals that Myfanwy collects because the shape of the shaving tells her about the cutting. Uniform ribbons mean smooth cutting. Broken ribbons mean the bar is chattering. The bore takes 8 hours. 8 hours of grinding, cooling, measuring, adjusting, measuring again. At the end, Myfanwy inserts her gauge, 4 points around the circumference. Top, 36.004 inches. Right, 36.005 inches. Bottom, 36.004 inches. Left, 36.003 inches. The variation, 2/1000ths of an inch. Better than Watt's specification, within the thickness of a worn shilling, equals 1/16 of an inch, equals 62 thousandths. 30 times better than specified. The bore operator, a veteran of 20 cannon borings, wants to move to the next casting. The schedule is tight. The cylinder is close enough.
It's within specification by a factor of 30. It's more than good enough.
Within specification isn't the question. The question is within tolerance.
The cylinder ships to Soho, iron, bored true, measured by Myfanwy Holt and accompanied by her measurement certifications. A sheet of paper listing the bore diameter at 12 points along the cylinder's length, each reading to 3 decimal places. Nobody at Bersham has ever sent measurement certifications before. Wilkinson shrugs. He doesn't see the point. Myfanwy insists. The measurements are the precision. Without documentation, the numbers exist only in her head. With documentation, they exist in the world. At Soho, the cylinder is installed in a Watt engine. The piston, machined to fit the bore with a clearance measured in hundredths of an inch, slides into the cylinder for the first time. Watt pushes it by hand. It moves smoothly, no drag, no play. The fit between piston and bore is the mechanical equivalent of a well-made joint in furniture. Tight enough to hold, loose enough to move, precise enough to seal. The engine runs. Steam enters the cylinder. The piston rises. The separate condenser, Watt's innovation, the device that makes the engine efficient by condensing steam in a separate vessel instead of inside the cylinder, creates a vacuum. The piston falls. The beam rocks. The pump pumps. And the steam, contained by the precision bore sealed between piston and cylinder wall by the 0.002 of an inch tolerance that Myfanwy measured and certified, doesn't leak. Doesn't leak. 2 words. The 2 most important words in the history of the steam engine. The separate condenser only matters if the steam stays in the cylinder long enough to push the piston. If the cylinder bore is rough, the steam leaks past the piston and the engine wastes fuel. Newcomen's engines, bored freehand, tolerances of 1/8 inch, lose 40% of their steam to leakage. Watt's engine, bored by Wilkinson's machine, measured by Myfanwy's gauge, loses less than 2%. The difference? The Industrial Revolution. Wilkinson has already commissioned his iron coffin. He mentions it at dinner, casually, the way another man might mention a new waistcoat. Iron coffin, iron memorial, iron obsession, iron legacy, iron future. The man sees iron the way Myfanwy sees measurement, as the material reality that underlies everything. Colette receives an order for 50 cannon. The boring machine will be busy, alternating between engine cylinders and gun barrels, between the peaceful and the destructive, between the tools that build civilization and the tools that destroy it. The same machine, the same bore, the same precision. The difference is what goes through the hole, steam or shot. Myfanwy doesn't resolve this contradiction. She measures it. The cannon barrels are bored true, the engine cylinders are bored true. The measurements go into her ledger. The same columns, the same 3 decimal place readings for both. She is the standard, and the standard doesn't judge the purpose of the bore. It judges the accuracy. Eleri, Myfanwy's mother, blind, sitting by the hearth with her filed-down fingertips that can feel a ridge of 1/1000th of an inch, runs her hands along a piece of bored iron that Myfanwy has brought home. She traces the interior surface, feels it. Her touch is more sensitive than her daughter's gauge. She can detect variations that the instrument misses. The tiny ridges left by the cutting head, the microscopic evidence of the bar's passage through the iron.
It's good. Smooth. The bar ran true. What is it? Cannon or engine?
Engine.
Good. I prefer engines.
Wilkinson's boring machine is copied across Britain within a decade. Every major foundry installs one. The precision it provides, the accuracy that makes Watt's engine practical, that makes industrial machinery reliable, that makes the Victorian engineering revolution possible, spreads from Bersham like a ripple from a precisely bored hole in the surface of history. The hole is not nothing. It's the shape of the future. 3 feet in diameter, 4 feet long, bored true to 1/100th of an inch by a machine powered by water and measured by a woman with a gauge and the stubbornness to insist that invisible precision matters more than visible power. The cannon fire and the proving ground behind Bersham. The engines breathe in the factories across England. Both owe their function to the same bore, the same machine, the same measurement. The contradiction doesn't resolve. It just continues. War and peace, destruction and construction. The cannon and the engine, both passing through the same precise hole that Myfanwy Holt measured and found to be true. True, the most important word in measurement. True means accurate. True means aligned. True means the bore is what it should be and the engine will work and the future will arrive. Myfanwy's gauge is still in her workbench drawer at the end of the day. Tomorrow she'll check it against the standard. The standard won't have changed. The gauge might have, 1/1000th of an inch maybe, from temperature. She'll adjust. She always adjusts. That's what measurement is. Constant, patient, obsessive adjustment toward a truth that never quite arrives but must always be pursued.